Hello, I'm Armin Sadeghi, and I'm going to talk about our paper on approximation algorithms for distributed multi-robot coverage in non-convex environments. My co-authors are Ahmad Asghar and Stephen Smith. The general question that we are trying to answer is that consider an environment, events happening in the environment, or a task coming in the environment. We know the spatial distribution of the events. We have a set of robots, and the question is, what is the optimal strategy for us to distribute these robots in the environment such that we m- maximize the sensing quality of the robots in the environment or minimize the time to respond to the tasks that arrive in the environment. For instance, in forest fire monitoring, we have a set of drones. They are equipped with cameras, and we want to minimize the distance of the event location to a closest robot such that the quality of a camera picture taken from each part of the environment is maximized. Or in an urban scenario, we have a set of tasks for repair requests arrive over time, and we want to distribute our repairmen or the robots in the environment such that we minimize the time to respond to these tasks. First, I'm going to talk about the problem in continuous environment. This is a very well-known problem. It's been studied extensively in the literature. So we have this continuous environment, convex or non-convex, a set of robots, a distance matrix, basically distance of the locations, density function representing the probability of event happening at each location, and a sensing cost function. The sensing cost function is our measure of the quality of servicing an event or measuring or sensing an event. The sensing cost function is a non-decreasing function of the distance. Basically, if the location distance of the location of the event and the robot that has been assigned to service that event is large, then the sensing cost will be large. The global objective here is to minimize the total sensing cost for the events in the environment. So we assign each location to the closest robot, then the times the probability of event happening at that location, and we sum over all the locations in the environment. So basically, the question is that what is the set of locations for the robot such that this objective is minimized? The same problem in discrete environments is defined on a metric graph. So we have a metric graph, a set of m robots, a weight function, basically this discrete version of the density function, and the similar sensing cost function. The objective here is that we minimize the total sensing cost of the events in the environment by the robots. So we want to find a subset of vertices for the robots to locate, and we assign each location to the closest robot times the probability of event happening at that location, and we sum over all the events in the environment, all the vertices in the environment. The conventional method for this algorithms and its different variants of it actually follow the same similar idea. We partition the environment by Voronoi partitioning. Basically, we assign each location to its closest robot. Then we use this Lloyd's-based descent algorithm to converge to a locally optimal solution. So each robot, in a distributed manner, finds the centroid of its Voronoi cell and moves towards it. The adaptation of this algorithm, the conventional method, to discrete environments would be we partition the environment, we basically partition the graph to a set of subsets of vertices, and each subset will be assigned to a robot that is closest to that subset. Then each robot will move to a vertex in its own partition such that it minimizes the sensing cost of the vertices inside its own partition. These algorithms are very good and they will converge to a locally optimal solution. But the problem is that there is no guarantees are how good these algorithms are versus the globally optimal solution. So our goal here is that we provide an approximation algorithm and we bound the difference between the solution that the proposed algorithm for our work versus the globally optimal solution. Prior to providing our approximation algorithm, I'm going to make some assumptions. First, Sensing cost function is a sub-additive function. Basically, the function over the sum of two arguments is less than sum of the function on each argument. I'm going to provide the reason behind this assumption later. The second one is the communication range. The communication range is approximately twice the conventional method. In the conventional method, each robot is a neighbor of another robot if they share an edge for their Werner cell. So consider this case, this the convex environment, the robots are shown with dots, and the Werner partition of the environment is shown. In the conventional method, the neighbors of the red robot is shown by the green robots. For our scenario, we take the maximum distance of the points inside the partition of each robot, and the distance from that robot to that location, we call it RCOM. Any robot within 4 times this distance is a neighbor of the robot. So these new robots in the environment. I have to note that we don't need this results in practical use. We only need this for providing theoretical results on the bounds of the worst case scenario. We will later show in the practice that with the conventional method, our algorithm performs very well. Now we provide the high-level idea behind our approach. Given a discrete environment coverage problem, we propose a distributed approximation algorithm, and we show that the final result of the approximation algorithm is within the 5 times of the globally optimal solution for the discrete environment coverage problem. What if we have the continuous problem? We sample it. We sample the environment and construct the discrete coverage problem. The sub-additivity of the sensing cost function will ensure that the resulting discrete problem is on a metric graph. Then we apply the distributed approximation algorithm for the discrete environment problem, and we show that the final result is within the 5 times of the optimal solution for the continuous environment plus some slack, where the slack is a function of how densely we sampled the environment. Now, what this approximation algorithm in distributed manner is based on? It is based on a very well-known centralized algorithm for discrete environments. Take this coverage problem in discrete environments, the centralized method. It starts from a solution, shown here with yellow locations. Then we do a swap. Basically, we swap a vertex in the solution with another vertex in the graph. If the new set of locations provide a better coverage, then we call that a valid move. We keep doing that valid moves until there is no other left. And it's been shown that if this approach converges to a locally optimal solution, and the result is within a 5 times the optimal solution. But how we can do this in a distributed manner? So our algorithm tries to make these moves in a distributed manner. For instance, take the configuration of the robots on the left. If we want to make the green move in a distributed manner between the robots yellow and green, then they don't know about the location of each other because they are not neighbors. But we can break down this green move to a set of smaller local moves. First, the green robot moves to a location inside its Werner partition. Then it will ask one of its neighbors to cover for him. Basically, it will ask one of the neighbors to go to the previous location of the robot. This process will continue, and each robot will ask its neighbor to cover for it until the yellow robot will cover for one of its neighbors. And the final configuration is shown in right. This was the basic idea of the algorithm that in a distributed manner. And we show that this algorithm will converge to a locally optimal solution within the 5 times the globally optimal solution in discrete environments. Also, we show that in continuous environments, it will converge to a 5 times the optimal plus some slack. That the slack is a function of the how densely we sampled or dispersion of the sampling. Another interesting result that we provide compared to the existing results in the literature is that our algorithm is a polynomial algorithm, which means that if it will terminate within the log of the solution cost in initial scenario divided by the solution in globally optimal solution divided by a polynomial, which is a function of the number of samples in the environment and the number of robots. To test out our algorithm in different scenarios, we first start with the convex continuous environments. We will test our algorithm versus the a very well-known Lloyd's algorithm, and the results are shown that here are the difference of the solution provided by the, our algorithm in two scenarios when we have the conventional communication range, i.e. the 2 RCOM, and the theoretical communication range 4 RCOM versus the Lloyd's algorithm. The results are the difference of the solution provided by these algorithms versus the solution provided by the centralized algorithm. As you can see, our algorithm, regardless of the number of the robots in the environment, provide very close to centralized algorithm solutions with both of the communication ranges. However, the Lloyd's algorithm will be stuck in a locally optimal solution if the number of the robots grows. For non-convex environments, I'm going to start with a simple example and show that how our algorithm improves the existing results. Shown in the left is a graph, and the weights are shown with the bars. And the initial configuration is a locally optimal solution for the conventional methods because each robot is restricted to move inside its partition, so there is no movement that will improve the solution. However, with our algorithm, we can break down the larger moves to smaller local moves. And the final result of the proposed algorithm would be on the right, which is also a optimal configuration for the problem. For more extensive simulation results, we use this environment. The distribution of the events in the environment is shown as well. We compare our algorithm to two existing algorithms. The green algorithm is a algorithm for discrete coverage problem, which is adapted to the non-convex continuous environments. And the yellow one is for the non-convex continuous environments. As shown here, our algorithms outperforms both algorithms, regardless of the number of the robots and the communication range. It's shown that our algorithm performs much better when the number of robots improves because the other algorithm will be stuck in a locally optimal solution. However, with breaking down the local moves with our algorithm, we are able to escape these local optimal solutions and approach to a globally optimal solution. For future work, we're considering the extension of the problem for heterogeneous scenarios. Now, we proposed an approximation algorithms for the case that we have homogeneous robots and single event type. Now, consider there are multiple events happening in the environment, and each has its own distribution, and each robot is capable of sensing a subset of them. What is the best strategy to distribute these robots in the environment such that we maximize the sensing quality for all the events in the environment? And we want to see to extend our proposed approximation algorithm and provide some approximation results for this problem. The other extension to the proposed algorithm is to investigate what is the response of our proposed algorithm versus the failures in a probabilistic or in adversarial scenarios. Consider an adversary is able to fail a subset of the robots in the environment. What would be the best reaction for our algorithm to this scenario? And thank you very much.